Greetings, everyone. This is my second attempt at this video. Hopefully the software won't crash again, but I think I made it better. So we're going to talk about the pre-calculus level of understanding for parametric equations and plane curves. That doesn't mean that you took a pre-calculus class where this was taught to you, but this does not involve any calculus. So that's why this is a pre-calculus treatment of this at the moment. Well, let's think about the equation y equals 4 minus 1/3 x squared, where x is a non-negative number for just a moment. Very simply, it's, we know the shape is a parabola, and because there's no horizontal shift, and we're looking just for non-negative values of x, it's just the right half of a concave down parabola that was shifted up 4 units and stretched or compressed by a factor of 1/3, depending on how you want to look at it. So with that in mind, we're going to take a look at this, and then we're going to change our understanding of this just a little bit. Now, in plane terms, x represents a directed distance of how far we are from the y-axis. And what I mean by directed distance is if the value of x is positive, we move in a certain direction to the right, and if the value of x is negative, we move to the left. Y represents a directed distance from the x-axis, positive being up and negative being down. You know all of those things. So if we go take a look at a graph of, if I can get on the right screen here, if we go take a look at a graph of the parabola, it looks something like this. Now, if you were to imagine a couple different cars traveling on this path, the location of the cars would be given by their x-coordinate and their y-coordinate, but not necessarily, no, not at all, rather, when they were at that particular location. So our function that we're given here gives us its location in the xy plane, but it doesn't tell us when it hits that location. When we get to this new concept of parametric ideas, I'm going to make an analogy to time. What if I wanted to know when a car got to that particular position? Let's go back and take a look at the graph really quickly, and let me put a couple different cars on there, aka points, and let me get them to move around a little bit. And I got my controls for my recording are in the way, so I'm going to shrink the screen down a little bit. Okay. Now I'm going to hit play right here, and you're going to see that there's an orange and a red car, and one is clearly moving faster than the other, okay? And let's actually just stop it right here. After 1.553 units of time, you can see the red car got to this position. So it got, almost 2.5, it looks like about 2 1/3 of the way, because 3 is right here, so about 2 1/3 away along the x direction, and it moved down from 4 to almost 2, so it's went almost 3 units down. But the orange car, if you will, only moved about 3/4 of a way to the right, because 1 is right here, and it didn't hardly move down at all, okay? And so this gives us a representation of what we're talking about analogously, to say that if we wanted to know when an object traveling along this path was there, I would need a third variable. We're going to call this third variable a parameter, okay? Hence the name parametric equation. And so if I wanted to describe the red position of the red dot, the red car, I could use this set of parametric equations, okay? So in this case here, t is representing time for us, but in general, a parameter doesn't have to represent time. And you can see the x-coordinate is given by 3/2 t. Now we said x has to be positive, and since x is 3/2 t is going to have to be, I said x actually non-negative, t is going to have to be non-negative also, otherwise x would have to be negative, and we already restricted against that. And then our y-coordinate is given by this 4 minus 3/4 t squared. And so the red position, we could start, identifying different time values. Oops, I got to switch to a marker. And of course, I'm having more tech issues. Maybe the red will work. All right, I had to pause the video and let my computer catch up a little bit. So if I, actually this is looking terrible. So let me try again here. Now, if I wanted to figure out where and when the object is in these locations, I can make a table. Okay, very simply, I can just start letting t be different values, and then I can go calculate the locations for the x coordinate and the y coordinate by plugging in t values. So if I plug in 0 for t, I would get 0 for x, I would get 4 for y. And if you go back over here to the graph, and we go when where they initially start, the red point is right there. The red and the orange are both in the same location at that moment, so they're on top of each other. But that's where it is at 0, 4. If I plug in 1, of course, I would get 3/2 here, and then 4 minus 3/4 is 3 1/4. I'm not going to do all of these necessarily. Let's do one more, and then I could plug in 2, and I would get 3 here, and 2 squared is 4, so this is going to be 1. And then we can get the location of the point or the car or the object or whatever at these different values of t. Now note the t variable is not represented in the graph. We only have an x-axis and a y-axis, so we only are looking at its location, and then we're just representing its location by a point at different times, and the point's just moving its location at different values of t. But t is not an axis in our graph. Okay. Now I could use a different set of parametric equations that would give me the same thing. The orange point is being controlled or is obeying a different rule here, and it looks like this. I guess I can put that as 1/12. I didn't reduce it in my head, but now I will reduce it. And it looks like this, okay? And I should call this one x1 and y1 over here. And I could do something similar and calculate the coordinates of x sub 2 and y sub 2 by plugging in the same values um, for t. In fact, it might be worth doing. So let me make another couple columns here. X2 and Y2. It's going to be real skinny so I can fit them on the screen. This is 0, 4 again, but now when I plug in 1, we're going to get a half. When I plug in 1 over here, we're going to get 3 and 11/12. So it hardly moved down after 1 unit of time. It moved a little bit to the, or used half a unit to the right, where this one moved 1.5 units to the right. At 2, this one would be 1 unit to the right, where this one was 3, so 3 times as far. If I plug in 2 here, this is what, 1/12 times 4, so 1/3, so this is going to be 3 2/3. And you could see, I got some work already preloaded. Anyway, so you can see that the second point is not moving as quickly along the curve as the first. And we saw that over here. If we let the parameter play out, I'm calling the parameter A because if I use T, it's a long story. It's a Desmos thing. But you can see that the orange point's moving much more slowly. Oh, so I just did that. Okay. Now what I have here is how Desmos represents their parametric equations. You can type in 3/2 t, which is the x sub 1 on the other screen, and then for y sub 1, comma 4 minus 3/4 t squared. So they just put it in as an ordered pair. I have values for t because they default to 0 to 1, which is not going to be a whole lot of curve. But watch when I do this. It covers, they both turned on. I didn't mean for that one to turn on just yet. The purple one covers the curve exactly because this set of parametric equations covers the same curve, the same locations as the original parabola. Same thing if I turn on the path for the orange point, it's the exact same path. Okay, it's traced out over a different amount of time, but nonetheless, it's the same exact path. All right, so what do we know so far? A set of parametric equations can give us some curve in the xy plane. The parameter is another variable not represented in the curve, okay, or not represented by an axis in the curve in the picture of this. And if we want to see the effect of the parameter, we should look at points along the curve at different values of t. We'll talk more about that in just a moment. There's something called orientation that I'll talk about with our next example. But let's go down here and give you a definition. I'm not going to leave this up here very long. You can pause the video and copy this down. But I'll read it real quick. So this is the definition of a plane curve. If f and g are continuous functions of t, so we need continuity here, on an interval I, then the equations x equals f of t and y equals g of t are called parametric equations, and t is called a parameter. The set of points x, y obtained as t varies over the interval I is called the graph of the parametric equations. Together, the parametric equations and the graph are called a plane curve. Okay. Again, this is all the pre-calculus understanding that we have. So pause the video if you want that, want some more detail, or if you want to copy that down in detail. So for example number 1, and I had worked this out and then the program crashed, and so I'm doing this again, but that's okay. Sketch the curve defined by the parametric equations x of t equals t squared minus 2t and y of t equals t plus 1. Now I could do that by creating a table, and I could let t vary for different values. Now I have no restrictions on x or y, so there really is no restriction on t, so I'm just choosing some numbers around 0. Take those values, plug them in to the x function, plug it into the y function, calculate x and y, and then of course I would just graph these set of points right here. I would not graph t in the picture. Okay, I would just graph those points. Let's go to Desmos and see how this would look. I did post a video where you can figure out how to graph these things on your TI-84/83 or your TI Inspire. It's a short video, but you can go check it out. All right, let's turn all that stuff off, and then let's get down here to this one. So this set of parametric equations looks like this, okay, and you can see the table of values here as well. So we have, t squared minus 2t, comma, t plus 1, and it traces out this curve, this red curve here. I did plot some points. The t-values I put in the third column because of the way Desmos reads things. I want it to read the x and y here to plot those points properly. So that's why it's listed that way. But the t can be listed as the first column since it's the one that's the input to those two when you write it down, okay? Now I want you to watch as the point, the green point, travels along the curve. Notice notice the direction in which it's traveling. The direction in which it travels as the parameter increases is called the orientation. Okay, and I don't have the ability to draw on the graph here freehand, but if I did, I would add some arrows indicating the direction at which the curve is traced out for increasing values of the parameter. So in other words, just in a few places along the graph, maybe here, in here, and then a few on the upper branch, here and here, I would put some arrowheads indicating that the curve is traveling in this direction. You could clearly see it with the point, but if this was a static picture, you want to include arrows on it so that the reader of the graph knows the orientation, meaning the value, the direction the curve is traced out for increasing values of the parameter. All right, let's go on to a different example. Let's go to example number 2. All right, with example number 2, I don't have anything below there. Let's see. Same thing. I want to sketch this set of parametric equations. Again, I could make another table. I could go use technology. I'm going to resort to using technology. And so let's go back over here to the graph. I'm going to shut the point off so it's not moving at the moment. And that example is actually right here. And watch the graph. Oh, notice there, it actually covers the curve exactly. Okay. Covers the same path. Okay. Why does it cover the same path? Well, it defines the same set of points, although it does so over different values of t. Let's go back up here for just one moment. The red graph was traced out between values of t between -2 and 4, where the green graph would be traced out for values of t between 2 and 14. So the red graph is traced out within 6 units of the parameter. If this is time, then within 6 units of time, maybe 6 seconds or 6 minutes or 6 hours or whatever the units of time are, where this one's traced out in 12 units of time, if t was time. So obviously the second tracing would be done slower than the first. If these were two race cars, then the race car that would create the red graph would travel that red path faster than the one tracing the green path. I did set up the point for the green one. Um, I guess I could really quickly if I just duplicate this like this and then change all these T's to B's, and then I could turn that on and you could see it. Whoops, not BB. That's going to mess things up. Now, this point here, they're both green, so that's not going to be very helpful. So let's make one orange. And if I turn B on, oh, I know what's going on. It's different values of T. That's why um, T goes from 2 to 14. So you can still see it's moving slower. I guess that's probably why I didn't set it up the original way, because I didn't set it up for equal values of T. So they're starting at different times. So you can think of them as two runners, but starting at different times to trace the track. And I didn't start them at the same time. But anyways, I think you could clearly see that the orange one is moving more slowly than the green one, which is the point anyways. Now, one more interesting thing about the parametric form, notice that the curve traced out here is not a function. Okay. Now this gives us parametric equations gives us an easier method. I don't know if easier is the right way, but it gives us a method for representing graphs of equations or items that are not functions, graphs of relations, much more efficiently typically than function notation. Okay, or thinking things as functions. But remember, if I want to find the inverse of a function, I have to switch the x and the y. Notice what I've done here in this ordered pair. I've switched the x's and the y's from this green graph. Okay, just switch their locations. Now, what happens when I turn this on? Well, that might be a little hard to see. Let me do this so things are a little bit more equally spaced. Can you see it? If you can't see it, let me do this. Can you see that symmetry there? Let me turn that off. Turn that off. The red one's still on. But anyways, you can see the symmetry, the reflection symmetry about y equals x. To get the inverse of a set of parametric equations, you just got to switch the x function and the y function, and the inverse is given immediately, much more quickly than going back to integrated 3 or whenever you learn how to find inverses. You have to switch x and y and solve for y, or undo all the steps and then redo them. This is much more efficient. All right, here's another example. Sometimes we use theta, an angle measure, as our parameter. So what would the graph of this set of parametric equations look like? 2 cosine theta for x and 2 sine theta for y. Well, let's go take a look. There it is. It's a circle. It's a circle of radius 2 centered at the origin. Now, if you go to type this in your calculator, you're going to want to do a zoom square. So you're going to go to your viewing rectangle, your zooming rectangle, and choose zoom square. Otherwise, it will look like an ellipse, probably. So you're going to have to zoom square if you want it to get like a circle on your calculator. I had to use T instead of theta because that's a Desmos thing. I tried theta. Desmos didn't like it. T for parametric equations in Desmos. That's going to have to be part 1, ladies and gentlemen. I'll give you a part 2 for the rest of this pre-calculus treatment of parametric equations, the little bit we need to know.